Okay, well, good evening. Welcome to the 77th Annual School of Earth Sciences Bonacker Distinguished Lectures. My name is Matt Saltzman, and as our school director, I'll be giving some brief words on the Bonacker series and its long distinguished history. I'll then pass the mic to Gretchen Ritter, the Executive Dean of the College of Arts and Sciences, to introduce our speaker, Naomi Oreskes. The Bonacker lecture series dates to 1937 and is named after John Adams Bonacker. Bonacker was both the chair of the geology department at Ohio State and also the state geologist, which he took over from Edward Orton Jr. in 1906. Bonacker's geologic map of Ohio, which is pictured here, stood as a reference for 86 years before needing revision. His research on building stones of Ohio, such as that make up Orton Hall, remains an important resource to this day. And thankfully for us, he established the Bonacker Endowment in his last will and testament, which we use to support this speaker series. The 77 names shown here have included luminaries in subjects ranging from the theory of evolution to the theory of plate tectonics, from planetary science to climate science. And I just want to highlight a few of these distinguished lecturers. Harold Urey gave the Bonacker lectures in 1950, was a Nobel Prize winner who discovered deuterium and pioneered studies of the origin of life. Ursula Marvin, pictured here in her extreme cold weather gear, was the first American woman researcher in Antarctica to hunt meteorites. Our own Lonnie Thompson, Ice Corps pioneer, hunter, and gatherer. Former Senator Al Gore gave the Bonacker in 2004, and NASA scientist James Hansen in 2008. These two have arguably done as much as anyone to raise awareness of global climate change. And Al Gore has actually written a foreword for Naomi's recent edition of her book, Merchants of Doubt. Susan Solomon led an Antarctic expedition that led to the development of the theory of the ozone hole there. Kathy Sullivan, geologist, astronaut, first woman to walk on space, and Worthington resident. 2018, Kevin Trenberth gave the Bonacker lecture. He was the lead author for the IPC assessment reports. And today, Naomi Oreskes joins this list, geologist, science historian, communicator, and as the New York Times called her, lightning rod. So with that, I want to turn it over to the Vice Provost and Executive Dean of the College of Arts and Sciences at Ohio State, Gretchen Ritter, to introduce Naomi.
Thank you, Matt, and hello, everyone. I'm Gretchen Ritter. I'm the Executive Dean and Vice Provost of the College of Arts and Sciences at Ohio State. And in the College of Arts and Sciences, we pride ourselves on being a place where we bring together different expertise and perspectives to try and tackle some of the great problems facing our society. Problems like climate change. We are working to understand its impacts on our environment, on human health, and our society, and to address those. Or problems like the COVID pandemic, which is wreaking havoc with our country and our world. Both of these challenges, of course, have had a significant presence in this week's presidential election. More than ever, we live in a time where science and the pursuit of truth have come under attack. And as scientists, scholars, and students, we increasingly find ourselves in a precarious position, needing to defend science in what is sometimes called a post-fact era. So as this tumultuous year comes to a close, and we look to 2021 and beyond, we might ask ourselves, why should the public trust science? And how could we rebuild that trust? This is a timely topic for this evening, And I am so pleased to have a very special guest with us for the 2020 Baunacker Lecture, who will be sharing her insights. Naomi Oreskes is the Henry Charles Lee Professor of History of Science and Affiliated Professor of Earth and Planetary Science at Harvard University. A world-renowned geologist, historian, and public speaker, she is a leading voice on the role of science in society and the reality of anthropogenic climate change. Dr. Oreskes is the author or co-author of 7 books, as well as over 150 articles, essays, and opinion pieces. Works such as Merchants of Doubt, The Collapse of Western Civilization, Discerning Experts, Why Trust Science, and Science on a Mission, American Oceanography from the Cold War to Climate Change, which is forthcoming from the University of Chicago Press. Merchants of Doubt, How a Handful of Scientists Obscured the Truth on Issues from Tobacco Smoke to Global Warming, co-authored with Eric Conway, explores scientific consensus and dissent, and was the subject of a documentary film of the same name produced by Participant Media and distributed by Sony Picture Classics. It's been translated into 9 languages and cited over 4,300 times, according to Google Scholar. A new edition of Merchants of Doubt, with an introduction by a previous Baunacker lecturer, Al Gore, was published this year. Her essays and opinion pieces on climate change have appeared in the New York Times, the Washington Post, the Los Angeles Times, as well as many other venues. Dr. Oreskes is an elected member of the American Academy of Arts and Sciences and the American Philosophical Society. She was named a Guggenheim Fellow in 2018. Adding to her accolades, she is now the 77th in a long list of distinguished earth science scholars to deliver the Baunacker Lecture at Ohio State. Thank you for joining us, Dr. Oreskes. And now I will turn it to Matt to give you your medal here.
Thank you, Gretchen. Naomi, on behalf of the School of Earth Sciences at Ohio State, I'm pleased to present you with the 77th Annual Baunacker Medal. I'll put this in the mail. I'll probably give it a few weeks to give the Postal Service some rest, but you'll get it.
Thank you so much. So it's an honor and a privilege.
Naomi, I think you're up.
You ready for me? Okay, thanks. Let me just share my screen here with you, and then we should be ready to go. Okay, can everyone see the screen? Yeah, okay.
Perfect.
Good. All right. Thank you so much. Well, first of all, let me just say it's really a pleasure to be with you here tonight, even if it's virtually. And I'm really sad that I can't be with you in Ohio. It means a lot to me to travel to other states, other universities, and have a chance to meet with faculty and students and talk about my work and other people's work and people's concerns. So, you know, this is the next best thing. I feel like I'm with you in Ohio. I told my family this evening that I was going to Ohio. They thought that seemed pretty weird, but I do try to feel as much as possible that I am with you here tonight. I also just wanted to say that it really is a huge honor to receive this award and to be a Baunacker lecturer. That list of previous winners is really a who's who in the history of geology. And on that list are many names of people that I have studied, that I have written about. And those of you who come to my talk tomorrow in geology will actually hear me talk about some of those previous lecturers. So it really is an honor to be among such distinguished people who have really contributed so substantially to our field. So with that, I thought I would start tonight by just saying a little bit about why I wrote this book, Why Trust Science, especially because the idea for this book developed about maybe 3 or 4 years ago. I didn't write this book because of COVID-19. And I'm obviously not happy that COVID-19 has happened and done the damage it's done. But it is the case that much of what I talked about in this book is relevant to our present situation. So I thought I'd just say a little bit about why I wrote the book, especially because I did write this book long before we ever knew that there would be a COVID-19. So the main reason I wrote this book was because for many years, I've now been given many public lectures on the issue of climate change. And in those lectures, I often find that people will say to me, I do a lot of work to explain the science, to explain how scientists have been working on the issue of man-made climate change for a long, long time, that this is not a liberal hoax invented by Democrats, that the history of the science begins 150 years ago in Ireland. But sometimes people will say to me, well, that's all very well and good, but why should we trust the science? And it seems to me that that's a legitimate question. We don't want, as scholars, simply to be handing people things and say, here, take it or leave it. We do want people to understand why we think this knowledge is reliable. And I don't think it's enough to just say, trust us, we're experts. One of my favorite lines in any film is the line in Ghostbusters where Bill Murray bursts into the room and he says, stand back, we're scientists. So I don't think that works. I think we know that that doesn't work. I think we know that our audiences actually deserve an answer to this question, an explanation of why our science deserves our trust, if indeed we think it does. The second reason has to do with a major question in the history and philosophy of science and in science itself, which is the problem of uncertainty. We all know, all of us who do science, who study science, who use science, know that science is uncertain. And there are two major reasons why this is the case. The first is that science is a process of learning and discovery. And that means by definition that if we're learning, it means that we will sometimes learn new things, and those new things will sometimes lead us to reconsider what we previously thought to be true. And that's a good thing. That's what it means to learn and to discover new things. But it means that we also have to find some way of understanding how to explain to people when our knowledge changes that it doesn't mean that what we thought that, that we made some giant mistake, that this is part of the learning process. But also in addition, there is intrinsic uncertainty in science, that no matter what we do, we can never say that something has been proven absolutely because the universe is complex, because the universe is probabilistic, and because we may learn new things in the future. David Jurafsky, a great historian of science who wrote the definitive book on the Lysenko affair, which was a dark chapter in the history of science when Soviet scientists rejected modern genetics, once wrote, the world's scientific community cannot claim absolute truth, but they can fairly claim that they are closer than anyone else to genuine knowledge concerning their particular fields of study. I agree with that. I think that's a very nice encapsulation of what we can and can't claim in science. But how do we know it? Can we reconcile the fact that science is inherently uncertain with this claim that scientists are closer than anyone else to the truth? And then a third reason for writing this book has to do with the work I did with Eric Conway when we wrote Merchants of Doubt. So in Merchants of Doubt, we tell the story of the deliberate generation of distrust, the deliberate attempt to confuse people by a group of people we call Merchants of Doubt. And the major finding of that research was that the tobacco and fossil fuel industries had deliberately tried to create public mistrust in science that showed the damaging effects of their products. So this wasn't a question of scientific illiteracy or a question of public misunderstanding of science. This was confusion, doubt that had been deliberately sowed by people for their own selfish purposes. And so for all these reasons, and probably some others beside, it seemed to me that it was important to try to take on the question, why trust science? And to take the challenge seriously and to try to answer it in an intellectually rigorous way. And then, of course, as we all know, now we face COVID-19. So my talk is not about COVID-19, but I think that it will be obvious the different ways in which what I'm saying is relevant to our present situation. And of course, I'm happy to answer questions about it after the talk. So when I think about the problem of scientific uncertainty, I think about the problem of Pascal's wager. Some of you may know that Pascal was a very famous mathematician and philosopher who lived in 17th century France. And Pascal worked on many important and deep mathematical questions, but he thought the most important question of all was not a scientific question. It was a theological question. It was the question, does God exist? And Pascal posed what today we would think of as the problem of a type 1 versus type 2 error. That is to say, he asked, what are the relative risks of believing in God if he doesn't exist versus not believing if he or she or it does? And Pascal said, well, that's pretty clear. It's definitely better to believe, because if I believe in God and there's no God, well, not much is lost. But if God does exist and I disbelieve, then I burn in hell for eternity. Now, to put this in secular terms, I had a professor in college who said that the way he thought about Pascal was that he clutched for the handrail of faith. So we can think about it as a kind of handrail, if you like. You may not need it, but it's always safer to hold on. But the problem of talking about faith is that scientists don't like to talk about science in terms of faith. This kind of language makes it seem as if accepting science, trust in science, is just a leap of faith. And indeed, sometimes it seems like it. Sometimes it seems like scientists just say, well, this is the way it is, and we're expected to just accept it. The problem comes in part because most of us, and I say us because I mean us, most of us have no idea how to judge whether scientific claims are true or not. We take it on faith or on trust from people who we think are trustworthy. And this is true even of most academics, because most of us don't know how to judge claims in areas outside of our expertise. So as a geologist, if I try to judge quantum mechanics or art history, I'm often no better off than any ordinary citizen. I may know just as little about art history as, my hairdresser. But like Pascal, we typically assume that the risks of accepting most scientific claims are smaller than the risks of rejecting them. But should we do that? Should we trust science? And if so, why? What is the argument for confidence in scientific conclusions? Well, the traditional answer to this question that you can find in many high school scientific textbooks is the scientific method. That is to say, the claim is made that scientists have a method, and that by virtue of using this method, they get true results. Now, if you ask people what the scientific method is, most people can't give you a clear answer, but usually it's something like what philosophers would call the hypothetico-deductive model, sometimes referred affectionately as the HD model. And what that simply means is that we develop a hypothesis. From that hypothesis, we deduce consequences, so logical consequences, and then we do something to see whether those consequences are true. We make observations in the natural world, or we design an experiment, or we do a randomized clinical trial. And if the consequences are true, then we're happy, we say the hypothesis is right, and we can move on to other things. If the consequences are not true, then we go back to the drawing board. And you can find some version of this presented in many high school textbooks. Now, I would say sometimes scientists do this, and we do actually have some good examples of it in the history of science. So I'm not saying that scientists never use the hypothetical deductive model, but I'm going to say that it's something that we only do sometimes. So there are some famous examples. Probably the single most famous example in the history of science is the proof or the confirmation of Einstein's theory of general relativity. When Einstein proposed the general theory of relativity, one aspect of that theory was the claim that space-time was not just sort of empty, but that it actually had shape, that it had a fabric, and that that fabric was bent in the presence of massive bodies. And so what we used to call gravity, Einstein actually understood as the bending of space-time in the presence of massive bodies. And scientists said, well, if that's true, then we deduce from that hypothesis that light moving past the sun will be bent, and therefore the location of a star, the location of a distant star, will appear differently. During an eclipse, that pathway will seem different because that light is being bent as it goes past the sun. And we wouldn't be able to see that normally, but during an eclipse, when the sun is blocked from view, we could actually see that. And so this observation was done. It was done by Sir Arthur Eddington in 1918. In fact, that prediction was observed. And so this was considered a brilliant confirmation of the radical theory of relativity. And this was written up in newspapers around the globe, including this article from the Times of London. Now, philosophers sometimes refer to this as the deductive nomological model, because academics always have to use fancy words when ordinary words will do, but also because ideally we don't want to just have a hypothesis, we want to have a law. So nomological means law-like. And so ideally we're trying to develop general laws, universal laws of nature that will apply in all cases. And again, so this is just to say the same thing, we're searching out universal laws. And again, we can find examples of this. So if we think again about Einstein, the universal law E equals mc squared, or from Newtonian mechanics, F equals ma, we do have general laws in science which we believe to be universally true. But there's a number of problems with this claim. And the most profound problem from a logical standpoint is it doesn't actually work. That is to say, the hypothetical deductive model is actually logically flawed. And it's flawed because of something that philosophers call the fallacy of affirming the consequent. Just because a prediction turns out to be true does not prove the theory that made the prediction. So I might say, well, if I throw dice of a certain number, it will rain tomorrow. And then it rains. Well, that doesn't prove that my throwing the dice caused the rain. I mean, there are many reasons why it may have rained. And my hypothesis is just one potential explanation out of many. In fact, if you think about it for even a few minutes, you know that false hypotheses can make true predictions. There are many famous examples of this in the history of science, but probably the most famous is the Ptolemaic system of astronomy. So many of you know that before Copernicus, Galileo, and Kepler, scientists and ordinary people generally thought that the Earth was the center of the universe. And they believed that the planets and the stars rotated around the Earth on celestial spheres. Today, we would look at this model and we would say that it's completely incorrect. We would say that we know that the Earth is not the center of the universe. And we would say that we know that the planets are not embedded into crystalline celestial spheres. And yet, the Ptolemaic model made extremely accurate predictions on the motions of the planets and extremely accurate predictions of celestial phenomena such as eclipses. In fact, it made more accurate predictions than the Copernican one did. So this tells us that just because the predictions come true does not prove that the theory is correct. There's a second problem which is closely related, and it's the problem of auxiliary hypotheses. By auxiliary hypotheses, we mean other assumptions that we are making, sometimes consciously, sometimes subconsciously, that are embedded in the test of the theory. Because when we test a hypothesis, we're never just testing the hypothesis on its own. We're also testing other assumptions that are built into the test. And we're also testing the reliability and the sensitivity of our instruments. So if we go back to the idea of the Ptolemaic model, Copernicus comes along and says, well, actually, I don't think Ptolemy is right. I don't think the Earth is the center of the universe. I think the Earth is moving. And then in fact, it's the sun that's at the center and the Earth is moving around in what we would now call the solar system. Well, people said, well, all right, if that's true, if the Earth is moving, we should be able to detect some of those, the effects of that motion. So logically, using the hypothetical deductive model, if the Earth moves, then there should be effects of that motion, and some of those effects should be discernible. And one of the effects that astronomers discussed was stellar parallax. Stellar parallax, you may remember from high school astronomy, or you may not, is the phenomenon where a star appears to be in a different place relative to the backdrop of different stars when looked at from different angles. Or, I mean, this phenomenon of parallax would be true for any object. So imagine that it's December and we look at a bright star, distinctive star like Polaris, and we see it against a particular backdrop of other stars. 6 months later in June, we look at that same star, and now we see it against a different backdrop. The angular distance in the apparent location of that star is the stellar parallax. And so astronomers said, well, okay, let's look for this. And if we see it, then we'll know that Copernicus is correct. So they looked and they found nothing. So what happened? Today, we would say that the Copernican theory is correct. So why did this test fail? Well, today we would say that the picture I showed you in the previous slide is a very misleading picture because it made it seem as if the star was very close and the parallax would therefore be very large. Today, we would say that the reality is something closer to this picture. In fact, even this picture is very exaggerated, that the Earth's orbit is very small compared to the distance to the distant stars. And so the parallax is very, very tiny, very hard to detect. And so scientists in the 17th century were unable to detect it because it simply was too small. There was an auxiliary hypothesis about the size of the universe, that in fact, the distant stars were much, much farther away than people realized. So the auxiliary hypothesis was that the Earth's orbit was large relative to the distance of the star. And that hypothesis was false. So if the auxiliary hypotheses are false, the test will fail, even if the original hypothesis is correct. Now, we can also say that in a way, there was a second auxiliary hypothesis, which was that the telescopes were sensitive enough to detect the parallax. In fact, it was not until the mid-19th century in the work of Sir William Herschel that telescopes were sensitive enough to detect the stellar parallax. But meanwhile, the Copernican theory had been accepted for a long time. So scientists didn't actually wait for these predictions to come true. They accepted the theory anyway, which raises a bunch of other interesting questions. So we might simply say that the hypothetico-deductive model is an oversimplified picture of the scientific method. And I think in some ways that's fair. The HD model is part of what scientists definitely do, but it's certainly not the whole story. But there's a bigger problem. If we look at the history of science, we see that a huge amount of science just doesn't follow the hypothetical-deductive model. An awful lot of science, including, I would argue, most earth science, is inductive. And by that, we mean the process of generalizing from observations. So the hypothetical-deductive model assumes that we begin with a hypothesis, but the inductive model assumes that we begin with observation, and that we make observations, and from those observations, we generate ideas which sometimes take the form of a hypothesis. Now, there's an interesting thing about this question about induction versus deduction, because it turns out there are fashions in science like everything else. We might like to think that science doesn't have fashions because science is science, but actually it does. And in the mid-20th century, inductive science would go out of fashion, particularly in the United States. Ernest Rutherford, the great physicist, famously dismissed inductive science as stamp collecting. And this was an idea that was promulgated by many American physicists. And I can even remember when I was in graduate school being told by professors who had been influenced by this idea that we should not do inductive science, that we should develop hypotheses. And what that meant in geology was a rather confusing thing, I thought. Indeed, physicists' hostility to inductive science made many American geologists and biologists think that they actually needed to change their science to make it more deductive and more quantitative. Now, in my mind, this was a project that was, I believe, misguided because, among other things, it contributed to the rejection of continental drift. But that's another story and a different book. But more important is that we know historically that some of the most important work ever done in the history of science was inductive. And the most famous example of that is Charles Darwin. I love to talk to undergraduates about Darwin because Darwin is very reassuring for anyone who's confused about their future. Darwin began college intending to become a physician, and he discovered that he hated the sight of blood. In fact, it made him sick. And he realized there was simply no way he was ever going to be a doctor. But he knew he liked geology, he liked being outdoors, and he liked the natural world. He was curious about the natural world. And so he managed to get himself a job through family contacts on the voyage of the Beagle. When Darwin went on the Beagle, he had no hypothesis. He really had no idea what he was doing. He just knew he didn't want to be a doctor. But he went on to become one of the most famous and important scientists in the history of science. and develop one of the most important theories ever developed in the history of science. So if you're confused about what you're doing and you know you don't want to be a pre-med, there is still lots of hope for you. So let me just say, so what did Darwin do when he went on the voyage of the Beagle? He observed, he looked, he collected, he thought. And through this process of observing and thinking, he began to generate a theory about where the diversity of life had come from, where these different species, how these different species had come to be. And through this inductive process, he eventually develops the theory of the origin of species through natural selection. Now, so those are sort of the two main kinds of activities that we can recognize in the history of science, induction and deduction, but there are a lot of other things too. Another thing scientists do is modeling. In the 19th century, physical modeling was an important activity in earth science because earth scientists were trying to understand how phenomenon happened. And one way that you might do that, since you couldn't actually see, since geology dealt mostly with things that had happened in the past, you couldn't see things that had happened in the Paleozoic or the Mesozoic, or even even things that had happened 10,000 or 100,000 years ago. But you could build models to try to replicate or reproduce the phenomenon that you saw. So this is a model of a Scottish geologist, Henry Cadell. You know, he's a geologist because he's wearing Wellington boots. He's got a rock hammer over here on the side and a nice wheelbarrow. And he's building a scale model to try to replicate phenomena that have been observed in the Swiss Alps, to try to understand how mountains form. Now, nowadays, when we talk about models, we don't typically mean physical models. We typically mean numerical simulation models, that is to say, computer models. And so this is an early computer model that attempts to explain what phenomenon, what causal factors could cause the observed global warming of the planet that we have witnessed in the last 50 years or so. So this is from the first report of the IPCC. And what this is a computer simulation in which the actual observed temperature changes on Earth are shown by this solid black line. These colored lines represent different forcing functions, that is to say, different causal factors that can influence the climate. And so we have things like changes in solar radiation, the increase in greenhouse gases, sulfate particles that can cause cooling. And what this model simulation shows is that the only way to reproduce what has actually happened is through all of the above. And you cannot explain the observed warming of the last 50 years without the forcing function, the warming effect of greenhouse gases. So in sum, my argument is not that one scientific method is good and other methods are bad. My argument is not that we should prefer one method or another. My argument is simply that there are different scientific methods, and that at different times, in different places, and in different branches of science, different fields, scientists have preferred different methods. The philosopher Paul Feyerabend is famously quoted, or sometimes people think infamously, as saying that the method of science actually is anything goes. Now, that's not quite what he actually said. What he said was that if you pressed him to say what the method of science was, then he would have to respond that the only principle that does not inhibit progress is anything goes. In other words, what he was trying to say, and what I think the history of science shows, is that scientists are innovative and creative. We choose methods that work for the problem, or that we prefer for various reasons. And sometimes those reasons are good and sometimes they're bad. And different scientific problems may call for different scientific solutions. So if we were a carpenter, we wouldn't think we could solve all of our problems with just a hammer. We would understand that carpenters have toolboxes that involve a variety of different tools, and science is no different. The idea that there would be one scientific method would be like imagining a carpenter who has only one tool. Rather, scientific methods are diverse, and different methods are appropriate for different problems. But then this raises a bit of a thorny question, because if the methods are very diverse, then the question becomes, well, do they have anything in common? I mean, why do we even talk about science? Maybe we should simply be talking about geology and biology and physics and chemistry and psychology. Well, I think the answer is that what all of these different methods have in common, what science has in common, and why it is meaningful to talk about science, as an activity is evidence. That science is an evidence-based activity, that no matter what science you're in or what method you're using, you're trying to collect, to generate, and to evaluate evidence. So I would argue that evidence is actually the key element of scientific knowledge, not method. That scientists can use all kinds of different methods, but what they all demand is that they are generating, testing, evaluating, and using evidence. But this then raises yet another question. And of course, academic research is always like that. There's always new questions. When we answer one question, it leads us to another. So the question here then becomes, who judges the evidence? And that, of course, is scientists. And then it might start to seem circular, because if scientists decide what the evidence is, scientists collect the evidence and scientists judge it, then how do scientists decide when they have enough evidence to say that something is known? And the answer to that turns out to be one that actually troubles a lot of people, because it doesn't seem as rigorous as they would like. But sometimes the truth just is what it is. Sometimes it isn't what we want it to be, but it is what it is. And I think that the truth in science is consensus. That scientific knowledge is simply the body of claims that have been agreed upon by relevant experts. Claim that experts have concluded or supported by sufficient evidence to say that they are true. In other words, claims that scientists have judged to be adequately supported by evidence. Or finally, we could say claims about which experts have come to consensus. And this is why consensus emerges as such an important category in our understanding of science. And why in my own work, I've written a lot about science, about the scientific consensus, for example, on climate change. Because if scientists have come to agreement, then it's telling us that scientists are saying, yes, we have enough evidence to say that this thing is true. And that is a judgment call, but it's a judgment of people who have worked really hard on the problem. So as I mentioned, this idea troubles some people. And I think one of the reasons why it troubles some people is that it seems to be an appeal to authority. And many of us were taught that the appeal to authority is wrong, that it's a logical fallacy, that we shouldn't be just believing something because someone says so. And in fact, in the beginning of my talk, I said we shouldn't believe science just because scientists say so. So I want to acknowledge that in some ways, science, this argument is an appeal to authority, but it's a very particular kind of authority. It's not the authority of an individual, no matter how brilliant or wise that individual is. So we do not believe in the theory of relativity because Einstein was a genius. We believe in the theory of relativity because enough different scientists have been able to use it in enough different contexts and test it in enough different ways that they have judged the theory to hold up. So it's the collective authority of scientific communities, of diverse experts who have weighed and judged the available evidence. And if you look at this picture and ask yourself, well, what are these people doing? What you see is that this woman is presenting evidence to her colleagues. Now, I have to say, I'm a little skeptical that these people are scientists because they look way too happy. But the point is clear. They are looking at evidence. She is explaining something to them and she is showing them some pictures or a graph, or maybe it's an X-ray. She is showing them evidence. So scientific knowledge, then we can sum up, is the intellectual and social consensus of affiliated experts based on the weight of available empirical evidence. This evidence is not generated and evaluated according to a single scientific method, but a set of diverse methodologies. These methods have changed with time, and they may be different in different fields. What's right for geology may not necessarily be right for epidemiology. But what we do know is that by and large, the methods that scientists rely on tend to be the ones that have stood the test of time. We can also think of science as a kind of jury, but in this case, it's a very special jury, a jury of scientific peers, a jury of people with scientific expertise. Other analogies we could think about would be crowdsourcing, but again, it's a very specific kind of crowd. And of course, this is one of the reasons why the internet and social media become such a problem for science, because now we have the proliferation of seemingly scientific claims out there, but we don't really know where those claims are coming from. So I want to make one more analogy and then I'll wrap up. And the analogy actually is to the modern car. The modern car is an incredibly reliable instrument. If you think about it, most of us, if we're not sheltering at home, get up in the morning, get in our cars, put the key in the ignition, or maybe now we don't even have a key, we just press a button and the car starts. So how is that? Why is the modern car so reliable? How did we get to the place where we could just get in our cars and take it for granted that they would work? Well, the answer is that the modern car is not the work or the result of a genius. It's the result of the accumulated expertise of the thousands of automotive engineers and experts who have worked on cars for the last 130 years or so. So it's the accumulation of all the wisdom, all the talent, and all the expertise. And I have to say, I need to update this slide because the last slide should obviously be a Tesla. So why believe in science? Well, we should believe in science. We should trust science because our scientific knowledge, like the modern car, is based on the accumulated expertise and experience, not of one genius, but of many different people working together. It works like our cars and our airplanes and our toasters and our contact lenses and our phones and all the other technology that we so take for granted in the modern world. It works because of accumulated expertise and experience. So we can think of scientific knowledge in a way as being an epistemic technology. It's a set of techniques that together work to produce knowledge. But this is a claim about science as a process. So what I'm saying then is not, we shouldn't trust scientists. We shouldn't trust individual scientists because they're scientists or because they're geniuses or because they've won prizes, but we should believe in science as a process because by and large it has worked well over time. So put another way, we should not trust scientists as individuals, but we do have good reason to have confidence in the process of which they are a part. And then there is one more important consideration, a very, very important consideration that I think takes on a certain poignancy in our current COVID-19 crisis. So if we return to Pascal and reconsider his question, what are the relative consequences of accepting a claim if it's false versus rejecting it if it's true? And you only have to sit with that for a few short minutes to realize that in many cases, this way of framing the question makes it completely obvious what needs to be done. So with respect to climate change, the issue that I have worked on and that so many of your good colleagues at Ohio State have also worked on, with respect to climate change, we should accept the results of climate science, because if we don't, and our scientific colleagues are right, then the consequences are dire. Communities will be destroyed, people will be hurt. But on the other hand, if it turns out to be a big hoax, well, then we will have created a better world for nothing. Thank you very much.
Thank you so much for your wonderful talk. At this point, I'd like to open the floor for questions. So everyone, if you could look at the bottom of your screen, you'll see a Q&A button that you can click on and type your questions in. We probably won't be able to get to all of them, but we will do our best. So the first question I have here is, what strategies do you recommend scientists use to inform the public about the scientific process and its legitimacy?
Yeah, well, that's a great question. Of course, we could do a whole second class or lecture about that. But I think a few things that we know from social science research, and I think that those of us who have done public communications recognize. The first thing is that communication is all about making connections. It's about making the human connection with people. And I think a lot of scientists have in the past made the mistake of thinking that, you know, we have to be the experts. And that means we have to play the role of expert. And that means we have to be very stern and very serious. And we have to not admit it if we don't know the truth about something. And I think we've learned, and all the evidence from psychology and sociology tells us this, that doesn't work. What works is to connect with people. And I think we experience this in our classrooms, right? If a student asks a question and we don't know the answer, we say, wow, that's a great question. Let me check on that and get back to you on Wednesday, right? To be a human being, to be open, to be approachable, these are all extremely important. The other thing that's really important is is to make the personal connection. And I've talked with a lot of scientists about this. One of my favorite stories about this has to do with my good friend and colleague, Ben Sander, who's one of the most important climate scientists. He's the person whose work showed that the observed warming couldn't be caused by solar variations in solar radiation. That led to the IPCC finding that most of the observed warming, that there had been a discernible human impact on the climate. So Ben used to always give very technical talks and never talked about his personal life. He never talked about why he went into climate science, never talked about why it mattered to him personally. And then he went through a personal change where he changed how he he changed how he was communicating with people. And he started talking about why he became a scientist and why climate change worried him. And it turns out he's a rock climber. So he started talking about his experience climbing. And he found that his relationship with his audiences changed dramatically. And people who previously, and particularly he started talking to people in the business community, people who previously had been skeptical, they'd find out, oh, you're a rock climber? Let's talk about climbing. And when you make those personal connections, those human connections, it helps you connect intellectually as well. And so I think to the extent that we are able to show our humanity and to show our vulnerability, that's a good thing. And of course, there's a gender component about this, because I think it's not a mystery why there are more women who work in science communication. As women, we've been taught that it's okay to be vulnerable, whereas men traditionally have been taught that that's not okay. So I think, men have to embrace their inner femininity and allow themselves to be vulnerable in order to connect with people.
Thank you so much for your thoughtful response. I really like that you brought up the gender component. I have another question here. How can we, as a generation who use social media, utilize it to encourage others to trust science?
Yeah, well, social media is a morass, and it's very, very tough. I think we all know that, one of the reasons we are facing the terrific problems that we're facing in the United States today is the way in which social media amplifies disinformation. And it's not enough simply to try to counter the disinformation with good information, because then you simply have this cacophony of claims and most people don't know what to do. So this is a very difficult subject, and it's an area that desperately needs more and better social scientific research. So any of you undergraduates who are trying to figure out, what can I do to help solve this problem? If you're at all interested in social media, there are tremendous research opportunities here. But one of the things we do know, and I rely here a lot on the work of John Cook at George Mason University, is what people are starting to call inoculation. And by that, they don't mean for COVID-19. They mean sort of mental inoculation against disinformation. And what that means is that if someone is supplying disinformation and I try to remedy it by supplying information, it doesn't work. It just becomes a big noisy mess. But if, on the other hand, someone is supplying disinformation and I say, well, hold on a second, that's disinformation. And let me explain to you how I know it's disinformation and who those people are and why they're doing what they're doing. That, it turns out, can be very effective. And part of the reason it's effective is because disinformation is essentially a con game, right? You're being conned by the tobacco industry who tells you that Luckies make you healthy, or that if you smoke Marlboro, you'll be more masculine and get the girl. That's a con, right? Smoking doesn't help you get the girl. Smoking kills you. And nobody wants to be at the losing end of a con game. So if you can show people that it's a con and give them persuasive examples, many people will say, well, heck, I don't want to be a sucker, right? And so that can be effective. And we do now have some research that's beginning to show the ways in which that works. So if anyone's interested, they should look up John Cook's work on this. It's called The Theory of Inoculation. You'd have to Google like inoculation disinformation to make sure you don't get information on COVID-19 vaccines, but the information is out there. And I think it's really important that we all educate ourselves on this issue.
Thank you. Here's another question. With the current COVID-19 pandemic, it seems that the medical and scientific communities can't always agree on what it is and how best to fight it. How do we determine who to listen to when trying to digest all of this information that is presented to us?
Great question. So this is very difficult, and especially it's difficult in an area where the problems are new. So in the case of climate science, one of the things I often point out to people is that climate scientists have been working on this issue for a really long time. Some people have heard of the Keeling curve, which is the graph that shows the increase in carbon dioxide in our atmosphere. Dave Keeling was a colleague of mine when I taught at the University of California. He began that work in 1958, and that's a very easy year for me to remember because that's when I was born. So I was born in the same year as the Keeling curve, so maybe there's some destiny here. So scientists, climate scientists have been working on this for a really long time. This isn't a fad. This isn't just a fashion. This is something that there's been really sustained work on. So now we go to COVID-19 and it's harder because it is new. And there's a lot of genuine uncertainties, especially not so much now. I think already in 6 months, we've learned a tremendous amount about this virus, but say go back to January and February when it was first emerging and we didn't know how deadly it was and we didn't know exactly what the routes of transmission were. So in those situations, we are in a tricky spot. And I think there's a couple of things that are helpful to keep in mind. The first one is about expertise. Experts are not always right. We know that. But non-experts are generally wrong, right? I mean, if you want good information about a medical question, you are very unlikely to get it from Fox News or the Wall Street Journal or Forbes or any organization that is not a medical or biomedical organization. So the CDC did make some mistakes. The World Health Organization did make some mistakes, but by and large, most of what they told us turned out to be broadly correct. So it is important to think about what is the source of information and do they have appropriate expertise? If I want business news, I will absolutely read the Wall Street Journal. But if I want to know about climate science, I absolutely will not. And the Wall Street Journal has said a lot of nonsense about climate change, and I think it's shameful, and I think their editors should, hang their heads in shame. I respect what they have to say about business. They should respect what climate scientists have to say about climate. So we need to be critical about the source of the information and what their claimed expertise is. Now, that said, it also means that experts have to really work hard to be honest when they don't know the answers. If we look at the World Health Organization missteps early in the COVID-19 crisis, one of the things that didn't help was that early on they told people not to wear masks. Now, to their own credit, they did not say masks don't work. What they said is don't go out and don't wear masks. It turns out the main reason they said that was because they were very worried. There was a shortage of masks for essential health workers. They were worried that people would go out and hoard masks. And so they told them not to buy and wear masks. Now, that was a misstep. I think they should have been honest and simply said, there's a shortage of masks, don't go out and buy them. But on the other hand, people did hoard toilet paper and cat food and pasta. So it wasn't crazy that the World Health Organization was worried about hoarding. But I think they needed to be more honest. And I think that when there are things that experts don't know, it's extremely important to simply say, we don't know yet. Because one of the things I have seen scientists do that I think is unhelpful is scientists will feel they have to say something. And I've been in many situations where I've actually heard scientists say, well, we have to say something. And I say, actually, no, you don't. It's perfectly legitimate to say, we don't know yet. We're working on this and we're going to get you an answer just as soon as we possibly can. But we'd much rather say, we don't know yet than to give you bad information. And so I do think that there were some missteps with CDC and who giving information that was not actually good information when they should have just said, we don't know yet.
Thank you. Building off of the idea of trust, we have a question here from our esteemed departmental hydrogeologist, Professor Audrey Sawyer. I noticed you use the terms believe and science together, something we sometimes shy away from. Are we wrong to shy away from combining these terms?
Yeah, that's a great question. And I think the fact that you see me using it in my talk shows it's very, very difficult to talk about these things without sometimes using the word belief. So I think that often scientists prefer to say, I accept the results of science, I accept the findings of science. And I think that's good. I think that's useful. And I think there's a certain specificity and accuracy about that kind of language. But I also think that at the end of the day, many people are really asking, why should I believe science? Or why should I trust science? And so that's why I'm using that language, because I am in fact trying to connect with ordinary people. And I think by framing it the way a lot of ordinary people think about it, I'm basically trying to invite people into that conversation. So I don't think it's wrong to say, if someone asks you, you're on an airplane and someone says, do you believe in climate science? It's perfectly fine to say, I absolutely accept the findings of climate scientists. I think there's nothing at all wrong with reframing it that way. But I also think you can say, yes, I absolutely do believe it, because these scientists have been actually right about just about everything. They've predicted virtually all of these things, and these predictions have come true. So why would I not believe it? And why would I not even use the language of belief? Because I do believe it. I believe both the findings, and I also believe in the process of science. I believe that science works, and I believe that we have, 400 or 500 years of history to back up that belief. So I can see why you might not want to use the language of belief, and that's fine if you don't, but I actually think it's okay to use it as well. And I have to say, by the way, my husband is a hydrogeologist. And I believe him when he tells me about water issues.
Thank you. How do you think we should encourage kids to think scientifically and to ask questions?
Yeah, that's a great question. Well, I work with the National Center for Science Education. I'm on the board, and the teachers we work with are so terrific. And I think that a lot of high school and elementary school science teachers are really on board on this issue, that they teach science as a process of learning and discovery. And so teaching children what it is to make an observation, what it is to collect data, what it is to record data, what it is to analyze data. This is what it's really all about, right? Because science is a body of factual information, but it's not just a body of factual information. And in some ways, the body of factual information is the least important thing to teach children, because it will change over time. So sure, we want kids to know some facts about the world. I want my kids to know how old the earth is, but teaching them about the process of learning and teaching them what it is to think about evidence and what it is to judge evidence. I think those are the most important things. And I'm proud to say that I think that most of the teachers that we work with at NCSE are doing that. But if there are any teachers in the audience who want help, NCSE has great programs in science education. We have a wonderful new program with people we call our teacher ambassadors, who are helping teachers around the country, especially with sticky and tricky topics like climate change and evolutionary science. And I believe we have a program in Ohio. So if anybody is interested in that, they should reach out to NCSE. Ann Reed is our executive director, and we have lots of great programs to support teachers in doing that really important work.
Thank you. Switching gears a little bit, can you comment on the relationship between data, especially massive data, and evidence in the age of data science and AI?
Huge question. Well, I'll say a few things. I think that big data is definitely a powerful tool. I think there are a lot of things that we are going to get smarter about by doing a better job of looking at more comprehensive data. And so I'm definitely an advocate of opportunities to collect large data sets, particularly in areas that have been lacking in good information in the past. That said, I think that some people view big data as a panacea, and it's not, right? Because data is only good as the interpretations you put on it. Data is not magic, right? Data has to be collected, data has to be analyzed. It's easy to collect bad data, it's easy to misinterpret data. So big data doesn't absolve you from the responsibilities of thinking critically, of analyzing information well, of using statistics intelligently. So more data is good, but you still have to treat it well. It's kind of like being in a kitchen. If you have lots of ingredients, that's great, but it's not going to guarantee that you make a good dinner if you just kind of throw them all together in a pot, right? As for AI, and machine learning, that's where things get trickier, right? Because a lot of AI has huge amounts of embedded assumptions. And I think one of the scary things that's happening in the world today is the way people are running ahead with AI and machine learning systems. And there's a growing literature on this, and I'm not an expert in this by any stretch of the imagination, but if you're interested in this, there are some really interesting books that have been written recently about the way in which AI embeds assumptions. So in a way, this is a sophisticated 21st century version of the auxiliary hypothesis problem. A lot of AI embeds subconscious bias. There's been a lot of interesting work about that. And it's especially problematic when it's used, say, for example, in policing. And I'm not remembering offhand the names of some books that I've seen on this topic, but if anybody's interested, we could follow up. I could make some recommendations for reading. So really important question, but I don't think it's at all the case that AI and machine learning will absolve us from the responsibility of thinking critically about tough issues.
Thank you. And just to let everyone know, we've got time for about 2 more questions. There's a follow-up question for that last one. If there is a time we need to give for scientific consensus to come together, is there therefore a period in which new science is risky to trust?
Yeah, that's a great question. And I actually argue that in the book. So I do think that one of the ways I was asked earlier about judging information. I think that one of the ways we should judge information is actually how new it is. And this is a really important thing to keep in mind, particularly in our world of, breathless media, because the media often report on new findings, right? The media are interested in news. And so by definition, if it's not new, it's not news. And so there's a tendency of the media to report on the latest study, this new study that just came out, today that says XYZ. Well, good science is never the result of just a single study. And it always takes time to sift through claims and counterclaims. And I think the media do us a huge disservice when they rush to publish an article on something. And then maybe a few months later, well, it turns out that finding didn't hold up. And then the public says, oh, see, scientists, they don't know what they're talking about. They're always changing their mind. Last week you said eat oat bran. This week you're saying don't eat oat bran. And so it gives this impression of terrific confusion. In fact, what makes scientific knowledge reliable is a body of evidence that has developed over time and for which there has been time to sift through it and to check it and to try to replicate it or test it in different ways. That's a slow process. And I think that our modern 24-hour news cycle, Twitter, Facebook, all this stuff is very ill-suited to explaining this process of sifting knowledge claims. So if you have to make a decision on something, then I would say absolutely, you should be skeptical of any claim that is very new. You should be more willing to trust claims that have stood the test of time. My own father was a biochemist and immunologist, and he used to say he had seen work, and he worked in a hospital, he ran a laboratory in a hospital, and he had seen how the drug companies were always coming and pushing new drugs on doctors, and often the doctors were very eager to try new drugs. And in many cases, these drugs had not actually been all that well tested. I mean, they'd gone through clinical trials, but often the clinical trials were small, maybe a few hundred people, maybe 6 months. Now you give this drug to millions of people, and you start seeing all kinds of side effects that didn't show up in the clinical trial. So my dad used to say to me, never take any drug that has been on the market less than 7 years, unless it's for a fatal disease. So my corollary of that is never believe any science that's been available for less than 7 years, unless it's for a fatal disease.
Thank you. And we've got one final question here, which is very timely and ties together a lot of the things that we've been talking about. With Thanksgiving being right around the corner and a lot of families gathering virtually, is it important for us non-scientists to fight the Thanksgiving dinner table battles over the legitimacy of science with our relatives? And if so, do you have any tips?
Yeah, well, Mike Mann has a new book, I think, that deals with this. And John Cook has a book on it too. I think he calls it the Uncle Joe problem or something like that. Although now Uncle Joe might be Joe Biden, so we might have to make it Uncle Max. Yeah, I get this question all the time. And of course, every situation is different. And, I don't want to tell anyone what to do. I mean, there's a time and place for everything. And you may decide that Thanksgiving is just a time to eat good food and watch football and just put off these issues for another day, right? Not every battle has to be fought every day. And sometimes it makes sense just to keep your powder dry. That said, I think if someone else raises the issue, it's very important not to be intimidated and not to flinch from standing up for what you believe is true, whether it's science or anything else. So if I'm ever in a situation where someone says, oh, I think that climate science is hogwash, or I think it's all a big hoax, I will never flinch from saying, well, that's just not true. And I'm sorry that you feel that way. And depending on how I'm feeling, I might say, well, why do you think that? And maybe if they tell me why they think it, then there might be an opportunity to explain why that's a mistake. Or maybe there's an opportunity for me to make a shameless plug and say, buy my book, which of course is the other thing you can do. And I have to say, I have had many people tell me, my uncle Sam doesn't believe in climate change, so I'm giving him Merchants of Doubt for Christmas. So there always is that option.
And then finally, I'd like to end on a hopeful note. And the audience is curious what hopes you have for the future of science.
Oh, well, that's better than the one I often get, which is what hopes do I have for the future of the planet, which is always feel like kind of a trick question because nobody wants, people sometimes will say, are you optimistic or pessimistic? And I feel like, that's a trick question because nobody wants to hear that you're pessimistic. But I have a lot of hope for science. I think that, for one thing, science has been around for a long time. I mean, depending on how you view it, we could say we can trace it back to the ancient Greeks. We can certainly say that science as we know it has been around at least since the time of, Kepler and Copernicus and Galileo. So, science has been around successfully operating and producing knowledge about the natural world for at least 500 years. And I think there's no reason to think that it won't continue. I mean, people have been writing poetry and creating music pretty much as long as there have been people. And in a certain way, there's been science as long as there's been people, because we're naturally curious people. So I think we will always have science. So I'm very optimistic about the future of science in that sense. And I also am optimistic because science is great. I mean, I was a scientist for many years. I did scientific research. And I made a decision to focus on some other things at a certain point in my career. But I've never lost that sense of wonder and excitement that I had when I was doing geological work. And, I still have all these like rocks that sit on my desktop. And I've got, I have my favorite rock right here, which is my favorite mineral is labradorite. So for the geologists in the audience, I have my nice little piece of labradorite here. Got a bit of banded iron formation. I mean, my rocks live with me. Here's another one. This is fluorite from Radium Hill, which is where the radium was mined in the 1920s for luminous clock watch dials. So, I mean, my rocks live with me because when you do science, it connects you to the natural world. And the natural world is amazing and beautiful. And there are so many wondrous things. And the fact that there can be a mineral that traps the light, you probably can't really see it, but the beautiful blue and green light that is refracted through the crystal structure of this mineral, labradorite, it's just kind of an amazing thing. It's like capturing a rainbow in a rock. And that sense of wonder and beauty in the natural world is something that I think is just precious. And I think it's the most important thing we can convey to our students when we teach science, and maybe the most important thing we can convey to the public when we talk about science too. And I think as long as we hold on to that sense of beauty and wonder and fascination, science will continue to thrive for sure.
Thank you again for being here with us, and thank you for answering our questions. And with that, I will pass it over to Matt Saltzman for closing remarks.
Well, thank you, Naomi, so much for being our 77th Bonacker lecture. That was wonderful. And I know it's been a long day, a long week, long month, long year for everybody. So I think we'll just end it here, and I'll look forward to your talk tomorrow at 1:30. Anyone can attend that as well on plate tectonics, the theory of plate tectonics. So very much looking forward to that. Thanks everybody for coming. We, I think, had about 440 people. So that was a really good showing. Thanks,
Terrific.
everybody.
Thanks. It's been a pleasure. Good night. See you tomorrow.
Yeah, bye.